So, continuing our work on Chapter 2, I want you to consider the following. So, here's something that in this course you'll have to do from time to time. So, let's just start off in 2 dimensions here. Okay. And I'll just go up here to some spot 2 over the y. And let's see. So I'll put in a vector that's, say, along this line. I'll let L equal 3x minus y. And here's my force vector coming off. And so x, the force vector is 4x plus 3y newtons. And we'll let that be theta. And somebody comes and asks you the following question. Find the force F along vector L. All right, so here's the force. The force is, it happens at this point. It's going off in this direction. 4 squared plus 3 squared. So we know the magnitude of F is 5 newtons. All right. But someone says, well, what's the magnitude of the force going along here? Well, hopefully you would just instinctively say, well, okay, well, let's see. The magnitude of the force is 5 newtons. If I knew that, I could simply say the F along L, the magnitude of what's along L would simply be 5 cos theta. That would be true. All right. But what's cos theta? How do we figure that out? So, well, we can do it this way. So we have a little question mark right there. But we can figure that out pretty easily. If we were to do F dot L, so this is known as the dot product or the inner product, and you should have seen that in math. So F dot L. Now, F dot L produces a scalar. And it can be computed 2 ways. F dot L, both of these give the same answer. Is the magnitude of F, well, we know that that's 5. The magnitude of L, that's 3 squared plus 1 squared, the square root of 10. Have no idea, that's 3 something. Cos of the angle between them. Oh, that's that thing we'd like to get. Now, of course, the other way you can do that, that you should all be familiar with from math, is F dot L is also the same thing as, if we go here, we can take the x coordinates, 4 times 3, and then we'll add it to multiplying the y coordinates. 3 times minus 1, so that'd be a minus 3. If there was a z, we'd multiply the z's together and add them on, so on and so forth. So that would be 4 times 3, there's the x's, plus 3 times minus 1, that gives us a 9. All right? So 9, and so we could now look at this and go, okay, 5 times the root of 10 cos theta must equal 9. Well, if you solve for that, you'd get cos theta is 0.5692. Do an inverse cosine and you'd wind up with theta is 55.3 degrees. All right. And now that we have that, we can compute the sine if we were so motivated. Actually, once we were here, we could have gotten very close to getting the sine because cosine squared theta plus sine squared theta equals 1. So if you know cosine theta, sine theta ain't far away, no matter how you look at it. All right, so let's see what we have here. What if I wanted, so here I said, what is the force F along L? Well, we got the magnitude. What if I wanted to express that as a vector? How would I go about doing that? All right, well, then I'd need a unit vector. So the unit vector along L so this, which is our direction vector. So I'd need 1 divided by the magnitude of L times the vector L will give me the unit vector. I'm just dividing this by its length, and that would give it to me. So let's see. Magnitude of L is the root of 10. 3 squared plus 1 squared square root, and that is 3.162. That's enough digits for me. So if I apply that, I would then have, here was L, so 3 divided by 3.162x minus 1 on 3.162y. And perhaps, yeah, let's call that meters. Give it a dimension. Well, it's just a direction. We don't care about the length here. All right. So now, if I want to have a force vector along here, which is why I took this out. Meters doesn't make sense right now. Okay. So therefore, F along L, where this is a vector, okay, I'll put another hat onto that, would simply be 5 cos theta, 0.562, all right, times 3 on 3.162x minus 1 on 3.162y. And that gives me a vector. This is, so if I wanted to have an equation for the vector along this length here, L, this gives it. Here's a vector equation for the force along L. And now I will put a unit on there, because that matters. All right? So, and it matters because if this is a force, the direction vector is just a direction. All right? When I'm doing this here, I'm not concerned whether it's in meters or whatever. It's just showing the direction. Once I put the magnitude on it, now because it's a force, we want to tell people what the unit is. All right? If you had the unit vector by itself and you happen to put meters on it, that would be fine. But once you go and this becomes a force vector, you got to have the right unit on there. So that's, just be careful to keep that straight. Okay, now, so we've done that. Suppose somebody said, well, okay, that's nice, you figured that out. What is, can you tell me F along L perpendicular? All right, so if we went up here, we could, this little dotted line, it would be, I'll call that L perpendicular. So that's a little L with a little perpendicular symbol up there. So what's the force along there? Well, that'd be F sine theta. Would just give us that magnitude. Let's just put the bars there for a magnitude for now. Okay. So let's see. The force magnitude was 5, and now we would have the sine of 55.3 degrees. Our angle there. Use a calculator, and you'd come up with 4.111 newtons. And now somebody says, okay, well, I want that in vector form. How would you do that? All right. Well, if you know L, it's very simple to find an expression for L perpendicular. There's an infinite number of them. Here's, having this in terms of x and y, here's how I would look at it. The slope of L, okay, it's the rise over the run. The slope is negative. It drops 1, and then the run is 3. So minus 1 over 3. So the slope is minus a third. Okay, if the slope of here is minus a third, what's the slope of something perpendicular? Well, from your geometry days, if I have two lines, if M and say N, so this is, let's let this be M, all right, and this N is the slope of the perpendicular. If you multiply the two slopes together, you'd get minus 1, all right? So if M is minus a third, what do I have to multiply to get to minus 1? 3. I need a line of slope 3. So once I know what this line is, that's given. If this slope is minus a third, slope right there is 3. I get that immediately. All right, so I will call, stay with L perp, slope, L perp is 3. So now I need a vector that has a slope of 3. And sometimes students are like, oh, how do I choose that? Well, it's really simple. Just create something with a slope of 3. This is rise over run. 3 over 1. L perp equals. So here's the, and this is y over x. X plus 3y. Done. Now, I need a unit vector to express this as a vector. So unit vector, L perp. So that's 1 squared plus 3 squared square root. So it's the same idea as before. X plus 3y. And there we go. We have a unit vector. So if I want to have a vector f along L perp, then let's see, its magnitude was 4.11, 4.11. 1 on 3.162x plus 3 on 3.162y. And we'll add in the Newton. And there we go. So, what we did in this problem is we need to be able to, given a direction in vector form and a force, which has a magnitude in a direction, we need to be able to express this force along another direction. Conceptually, very simple. We just do a projection. Is it a cosine, or we could have gone over this way to get del perp? It'd be a sine. Very easily done. Problem is oftentimes we don't know these thetas. How do we get them? We use the dot product or inner product, depending on what you want to call it. And that pops that out. That gives us theta. Now we can take sines and cosines, and it's all really easy. Given any given direction, once we know its slope, we can find the perpendicular direction. So if this becomes like an x in a new coordinate system, bam, we can get the y. Very easily, because the slope of these will be the slope of this times the slope of that. They have to be minus 1. Now, so we've done this for 2 dimensions. We're going to do this one more time, except now it'll be for 3 dimensions, x, y, and z. And that'll be the last problem we do, and chapter 2 will be gone. Catch you soon.